Let f be a differentiable function at the point P on the surface S given by capital F of x, y, and z equal to 0, such that the gradient of that function at a point is not 0. If you have that, the plane through P that is normal to that gradient is called the tangent plane to your surface at your point given. Also, the line through P having the direction of your gradient is called the normal line to the surface at point P. Theorem: if f is differentiable at a point, then an equation of the tangent plane to the surface given by the function, and again, this will be all the terms of an equation that's given collected on one side. So if the equation given is not equal to 0, then you want to make it equal to 0 at the point given. So it has the partial derivative with respect to x times x minus x sub 0, the partial of f with respect to y times y minus y 0, and finally plus the partial derivative of f with respect to z at the point given times z minus z sub 0. Any of these x, y's, and z's that have a 0 subscript, those are the point that'll be given. And we're going to set that equal to 0. So let's look at an example. Find an equation of the tangent plane to the hyperboloid z squared minus 2x squared minus 2y squared equals 12 at the point 1, -1, and 4. So first thing you do is you take your 12 over so that your equation has all terms on one side and define that as your capital F. And that's what I've done here. The partial derivative with respect to x will be -4x. The partial derivative with respect to y is -4y. And the partial derivative with respect to z is 2z. Plugging in the point given to each partial derivative, 4 times 1, -4 times 1, that's -4. -1 times -4 is +4. And then 4 subbed in times 2 is 8. These partial derivative values are the coefficients up here. So you have -4, and I'm going to come back down here, -4 times x minus 1 plus 4 times y minus -1 plus 8 times z minus 4 equals 0. Distributing, you get -4x plus 4. Inside here's a plus sign, so it's 4y plus 4, 8z minus 32. Collecting all your variable terms and then combining the constants, you get a -24. This equation is totally fine. If you want to reduce, feel free to reduce. I just chose to divide all of these by -4, and this was the equation of the tangent plane to this surface at that point. To find an equation of the tangent plane at a point on a surface given by a two-variable function, you can define capital F by take the function given and you'll move, essentially you're moving all your terms to one side anyway, but if you were to bring z over, it would be a -z. Then you can build your tangent plane by again doing partial derivatives times x minus the given x, y minus the given y, and so forth. This f sub z, it's totally up to you if you take the partial derivative f sub z. You don't really have to, because that's always going to be a -1, and that's what this negative covers. I chose to do it down here just to show you, but it's not required. So let's do an example of this previous definition. Find an equation of the tangent plane to the paraboloid z equals 1 minus 1/10 times x squared plus 4y squared at the point 1, 1/2. I'm going to define capital F to be, this part is your lowercase f of xy. And then when you bring that z over, it just becomes negative. So we have this format as our capital F. Taking partial derivatives, negative 1/10 times x squared is x squared over 10. Its derivative will be negative 1/5 x. 4y squared times negative 10 is a negative 2/5 y. That derivative, negative 2/5 y squared. That derivative will be negative 4/5 y. The z term, its derivative is negative 1. This one's not required. In fact, after this point, I just leave it off. Okay, our partial derivatives at the point given, negative 1/5 times 1, that's negative 1/5. Negative 4/5 times 1, that's negative 4/5. Again, nothing to sub here, so you can either write it or you can leave it out, either way. Now we can build our equation. Negative 1/5 times x minus 1 minus 4/5 times y minus 1, negative sign, z minus 1/2. Distributing, and then at this point you can leave your x, y, and z terms just as they are. You will need to combine your constants, but what I did was I multiplied all the way through by 10 because I have a load of 5s and a 2 for denominators. So I multiplied all the way through by 10, and I made a little note here. And then 2 plus 8 plus 5 is 15, but I chose to change all the signs. That way my variable terms will be positive. Then that would force the constant to be negative. Don't get in a real big bind over that. You can leave your x, y, and z terms as they are. Just make sure you combine all your constants together. I do want to make a note that the gradient provides a convenient way to find equations of normal lines. Remember, normal is another word for perpendicular. The gradient is normal to the surface given by the equation where all your terms are on one side, basically. Find a set of symmetric equations for the normal line to the surface. X times y times z equals 12. At this point, 2, negative 2, negative 3. Bring the 12 over so all your terms are on one side. That's your capital F. X, y, z minus 12. The gradient is the derivative of f with respect to x. So you'll take all three partials, and those will be coefficients of I, j, and k, the standard unit vectors. All right, and that's what I've done here. The derivative of the x would be 1, so that's yz. Derivative of a constant always goes to 0. Now the partial derivative with respect to y, that's 1 times xz. And then the partial derivative with respect to z, that will go to a 1 times xy. Subbing in the point given, we have the gradient of f at the point given, y times z, that's negative 2 times negative 3, that's positive 6i. X times z, 2 times negative 3, that's negative 6j. And then x times y, 2 times negative 2, that's negative 4k. The normal line at the point given has direction numbers, and you'll take your coefficients of I, j, and k. We did this way back in week 1. A, B, and C are the coefficients of I, j, and k. this is the blueprint for your symmetric equations, and we've done these. So it's going to be x minus 2 over a, y minus negative 2, that's y plus 2, over b, negative 6, and then z minus negative 3, that's z plus 3, over negative 4. Find a set of parametric equations for the tangent line to the curve of intersection of, we have an ellipsoid equation given and a paraboloid equation given at this point. We're going to find the gradients to both surfaces at the point given. Now the ellipsoid, I'm calling it capital F. Remember, I've got to move the 20 over, and I've done that here. And the paraboloid, I'm going to move the 4 over, and I've called it capital G, and I've done that here. The gradient is 2xi plus 4yj plus 4zk, and that's for the ellipsoid. For the paraboloid, it's 2xi, 2yj, 1k. Now, evaluating each gradient at the point given, we're going to plug 0, 1, and 3 in for x, y, and z respectively. 2 times 0 is 0, so there's no I term. 4 times 1, that's 4j. 4 times 3, that's 12k. For g, 2 times 0 is 0. There's no I term. 2 times 1, that's 2j. And then there's no z to sub in, so we don't have to plug that 3 in. 2j plus k. In this one, we had a z for a substitution. Now that we have our gradients, and remember those point in the direction of steepest incline, we will take the cross product of those. Remember how to do that from week 1. So take the coefficients. We have 0i, 4j, 12k, and I've put that here. 0, 2, and 1 for the coefficients in gradient g. Now when you work all this out using the cofactor expansion, you have negative 20i plus 0j plus 0k. Okay, now let's take these. These are direction numbers, A, B, and C. A, B, and C. The point given is your x sub 0, y sub 0, and z sub 0. So use them in combination. X will be 0 minus 20t. Y will be 1 plus 0t. And z will be 3 plus 0t. We get negative 20t, 1, and 3, and those are your parametric equations. The angle of inclination of a plane is defined as the angle theta somewhere between 0 and pi over 2 inclusive. 0 is parallel, pi over 2, that's perpendicular, between the given plane and the xy plane. K goes in the z direction. It is perpendicular or normal to the xy plane, and so we can write our formula as cosine theta equals the absolute value of n dotted with k over the magnitude of n times the magnitude of k. And since k is a standard unit vector in the z direction, that actually is equal to 1. So we can simplify this and do the absolute value of the dot product for our gradient, the the k standard unit vector. We're going to dot those, absolute value if required, if it's negative, over the magnitude of our gradient. And let's get to it. An example, find the angle of inclination of the tangent plane to the ellipsoid given here, this equation, at the point 2, 2, 1. Well, I'm immediately going to move this 1 over, and I can define my function f as all those terms that would be collected on the same side. Notice the 1 becomes negative. I'm also going to multiply all 4 terms by 12, and that gets rid of all the fractions. You can actually do that here in the beginning, is multiply all of it by 12, and then you move your 12 over. The gradient using this one would be 2xi plus 2yj plus 8zk. The gradient evaluated at the point given, so del f of 2, 2, 1, 2 times 2 is 4, 2 times 2 is 4, 8 times 1 is 8. When you dot this vector with the standard unit vector k, all you're going to have is 8 times 1. And why is that? Because the standard unit vector k has no I or j component, so really you're just doing 4 times 0 plus 4 times 0 plus 8 times 1. Grand total is 8. The magnitude of this gradient is square root of 4 squared plus 4 squared plus 8 squared, and I've written that here. That has a grand total of 96. Under the radical, 8 divided by square root of 96, rounded to 4 decimal places, and then theta is the cosine inverse of that value. You can actually leave this and do cosine inverse of this fraction, and your answer will be a little more accurate. Anytime you round a mid-problem, you lose accuracy at the end. So cosine inverse of either that fraction or this decimal will give you a little over a 35-degree angle of inclination. I hope this video helps. Reach out if you have any confusion on completing your homework. Reach out by email, phone, or stop by the office, and I'll be happy to help you out.